For today's lesson, you'll learn how to configure the built-in Wi-Fi of your ESP32 via the station mode and access point mode. You'll learn how to scan available Wi-Fi networks, connect to an existing network, and turn your ESP32 into station mode to serve up web pages to any connected client within the same network. You'll also learn how to create a standalone ESP32 web server that can be accessed by any device on a local network. At the end of this lesson, you will be able to conduct your own experiment to control sequences of the LEDs attached to your ESP32 through your laptop or phone's browser. Hi, my name is Joe Edgo, and welcome to Lesson 3 of the IoT Development Training Course with ESP32. For this experiment, you'll need the following materials: your ESP32 development board, 3 LEDs, red, green, and blue, 3 current limiting resistors, values could range from 150 ohms to 470 ohms, a couple of connecting wires, a breadboard, and a micro USB data cable. Our circuit connection is fairly easy. The blue LED is connected to GPIO2, the green LED is connected to GPIO22, and the red LED is connected to GPIO23. So, let's begin the concept. The ESP32 supports Wi-Fi protocols 802.11, B, G, and N, and it operates at 2.4 GHz. In Arduino IDE, we will be using the wifi.h library to handle the Wi-Fi capability of your ESP32. With this, we can use the ESP32 in either a station mode or a soft access point mode. So, what's the difference between these two modes? In station mode or STA, the ESP32 connects to an existing Wi-Fi network. This is the one created by your wireless router. It means that it is just another client to your routers similar to your computer, tablet, or phone. In station mode, your ESP32 gets its IP address from your wireless router's Dynamic Host Control Protocol or DHCP to which it is connected. However, in soft access point mode or SAP mode, your ESP32 creates its own Wi-Fi network, just like Wi-Fi router, and acts as a hub for one or more stations. In SAP mode, your ESP32 is the center of the network, providing connections to other devices like computers, tablets, or phones. It means that your ESP32 assigns the IP addresses to the clients. However, unlike a Wi-Fi router, it does not have an interface to a wired network to connect to the internet. Thus, such mode of operation is called soft access point. Also, note that the maximum number of stations that can connect to it is only limited to 5. Now, both the station and soft access point modes allow your ESP32 to act as a web server. Basically, it allows to store, process, and deliver web pages to web clients. So, let's start writing codes to explore these features. Let's have a program that scans all the available Wi-Fi networks within the range. So, I'll start by including the wifi.h library, and then I'll define 3 LEDs, red, green, and blue, at GPIO 23, 22, and 2 respectively. In the setup function, I'll set the pin mode of these 3 LEDs as output, then start the serial communication, and finally, set the Wi-Fi mode to station mode, Wi-Fi STA. Also, we need to disconnect from any existing access point if it was previously connected. Then, let's have 1 second delay before we continue. Inside the loop function, I'll print a message scanning available networks. Then, as a physical indicator in our prototype, I'll turn on the red LED and then turn off the green LED. So, to scan for available Wi-Fi networks, we need to call the scan networks function. Now, this function returns a number that represents the total number of networks found. With this, we can create a condition that checks if there is an existing network found. Then, I'll change my LED indicator, turn off the red LED, and then turn on the green LED. And in my serial monitor, I'll display the total number of networks found. After this, I want to display all the available networks found. And to do this, I need to create a for loop that iterates from 0 up to the total number of networks found, represented by n. And for each network, starting from network 1, I'll print its service set identifier, or SSID. This is commonly known as the network's name. Then, after this, close in parentheses, I also want to display the network's received signal strength indicator, or RSSI. It is a measurement of how well our ESP32 can hear signal from an access point or a router. The unit of measure is in decibels or dBm, and basically, the closer to 0 dBm, the better the signal is. And then lastly, let's also print the Wi-Fi's encryption type. If it is open, then I'll print open. Otherwise, print 3 asterisk to denote password protected. So let's have a short delay of 50 milliseconds for each network information to be displayed. However, if n is 0, it means that there is no available Wi-Fi signal being detected. So I'll turn off both the green and the red LEDs. I'll put a separator here, and then let's pause for about 5 seconds so we can investigate on the networks found, if any, before it loops back to scan again for all available networks. Okay, let's upload the code. I'll open my serial monitor, and as you can see, the red LED is turned on and a message scanning available networks is displayed. Then, the green LED is turned on and the 4 networks were found. Then, it repeats the same process after 5 seconds. So, network 1 here has the strongest signal relative to this ESP32. It is actually my phone's hotspot. And this is the one I'm using to record this circuit, so it's very close to my ESP32. That's why it has negative 39 decibels, which is very, very good. The 3 asterisk denote password protected. However, network 2 here is my Xiaomi repeater placed inside my room, and it has open authentication, and the signal is also pretty good. Well, typically, signal strength reading around negative 60 to negative 70 is good, while signal ranging from negative 90 and below is not good and very unstable. So, that's it for our simple Wi-Fi scanner. Now, let's create a simple Wi-Fi server. Actually, there's a lot of sample codes here, and let's check this Wi-Fi and then simple Wi-Fi server. So it says here that this program is a simple web server and lets you blink an LED via the web. And that we can turn on and off the LED via the IP address that is dynamically assigned by the router's DHCP. So it starts with the same directive, wifi.h. Okay, let's modify this code by getting 3 defined constants from our previous code and then paste it here. And then these 2 constants, SSID and password, correspond to our target network's SSID and password to which we want to connect. So, I'll want to connect to Jogo Galaxy and its password is 12345678. Then, this code sets the web server port to 80. In the setup function, I'll change this GPIO5 to red LED pin. Duplicate this code to include the green and the blue pin as well as output. And then, this wifi.begin initializes the Wi-Fi library's network setting and provides the current status. So, the next code block is a while loop. It checks if the Wi-Fi status is not yet connected to a network. It continuously prints this dot every 500 milliseconds. So I'll insert here the red LED indicator that blinks while it is trying to connect. By the way, this code is one of the simplest way to make the LED blink by reading its current status using the digital read function and then negating it. Now, once it gets out of the loop, it means that the ESP32 is successfully connected. This Wi-Fi.local IP function gets the dynamically assigned IP address to our ESP32. And when this happened, I'll turn off the red LED and then turn on the green LED. Finally, the web server can begin. So, inside the void loop, there's a couple of codes here with their corresponding explanation. So basically, this code listens for incoming clients. We will be using a web browser through this laptop or through my phone. Then, if you get a client, this string current line will hold the incoming data from the client. And then, this while loop will happen so long as the client is connected. Then, if there is a byte to read from the client, read that byte. And if that byte is a new line character, perform another check if that current line is a blank. That's the end of the client HTTP request, so send a response. Now, in here, the HTTP headers always starts with a response code and the content type. So the client knows what's coming, followed by a blank line. And this is the content of the HTTP response that follows the header. These two hyperlinks, response/h to turn the blue LED on pin 2 on, and then the /l to turn the blue LED on pin 2 off. And the HTTP response ends with another blank line. Now, this is where the control happens. This code checks if the client request was get/h to turn on the blue LED pin, or get/l to turn off the blue LED pin. Then, close the connection and repeat the entire process again to listen for incoming clients again. So, let's upload this code to see how it works. And as you can see, the red LED is blinking as it tries to connect to Jogo Galaxy network. By the way, I intentionally turned off my mobile hotspot so that you can see it connecting. Now, I'll enable my mobile hotspot and the green LED turns on and a message says Wi-Fi connected. And the assigned IP address to this device is displayed. So, I'll copy this one. And now, to test if the web server is working, I'll connect this laptop to this Jogo Galaxy network as well, so that they are using the same network. And then, I'll open a browser and paste this IP address. And you can see the content of the HTTP response. You can also verify this in the serial monitor that a new client was received, responded to, and then disconnected. So, when I click this link, the client request was get/h, and the blue LED turns on. And then, if I click the other link, the client request was get/l, and the blue LED turns off. So, for every client request, either to turn on or off the LED, the client gets disconnected and repeats the same process for another incoming client's request. Now let's have another example. And this time, instead of using a Wi-Fi server, we'll use the webserver.h library. Why? Because it has some additional methods that will help us to set up a server and handle incoming HTTP requests easily. Also, instead of connecting to an existing network, as we did in station mode, we'll create our own Wi-Fi network via soft access point mode. So, I'll define the name of my network, ESP32_AP. I'll also set the password to 12345678. And for this experiment, I'll be working with just the blue LED at GPIO2. Now, to configure our soft access point, we need to set an IP address. You can set it to your preferred IP address, but mine, I'll use the commonly used default router IP address, which is 192.168.1.1. Also, the gateway and the subnet mask. Next is to create an instance of our web server library so we can use its function. The constructor of this object takes port as a parameter. This is where the server will be listening to, and the default port for HTTP is 80. And now, you can access the server without needing to specify the port in the URL. Also, I'll declare and initialize our LED status variable. So, in the setup function, I'll set up the serial communication and then set the blue LED pin as output. And then we set up the soft access point to establish the Wi-Fi network by providing SSID and then password, as well as the local IP, gateway, and then the subnet mask. Now, in order to handle the incoming HTTP request, we need to specify which code to execute when a particular URL is hit. Thus, we use the on method. This method takes two parameters. The first one is the URL path, and the second one is the name of the function which we want to execute when the URL is hit. So, for example, when a server receives an HTTP request on the root/ledOn path, it will trigger the handle_ledOn function, which we are about to create later. So, we'll do similarly to handle the ledoff, as well as if the client requested for any URL beyond the specified server.on functions. It should respond with an HTTP status 404 not found message for our user. Now, let's start our server. We call the begin method. And to handle the actual incoming HTTP request, we need to call the handle client method on the server object. And depending on the request, this LED status variable could change its value. And this is the one that we need to check in order to change the blue LED pin state accordingly. Okay, I mistyped here the blue LED pin. And now, the next thing to do is for us to create these four functions that will handle the corresponding actions for each request. So, let's start with the handle on connect. This function sets the LED status to low and then prints a message LED status off, and finally respond to the HTTP request. Here, we use the send method of the web server object. Now, this method can accept multiple parameters, but in its simplest form, it accepts three: the HTTP response code, the content type, and the actual content. So, code 200 is one of the HTTP status codes which corresponds to the OK response. And then, we specify the content type as text/HTML. And finally, the content in HTML. Well, instead of placing a bunch of HTML codes here, I'll simply create a function getHTML that returns an HTML content and call it from here. So this getHTML function will be responsible for generating a web page whenever the ESP32 web server gets a request from a web client. So I'll start by creating a string variable, HTML code, and then this doctype declaration indicates that we are sending HTML code. So what we're going to do here is to simply concatenate HTML codes into a big string and then return it to the server.send function. So next to concatenate is this head containing the meta viewport element, which makes the web page responsive in any web browser. And then, of course, the title of the page. Now, I will not add any styles yet to make it simple. So I'll close the head and add the body section. I'll add headings of the web page ESP32 web server, and then a simple demo using access point mode. And now, depending on the value of our LED status variable, the HTML code will vary. If the LED status is high, which evaluates as true, we add a paragraph blue LED status on, then followed by a hyperlink to the root address /LED off that says turn it off. Otherwise, the paragraph will be displayed in the web page is blue LED status off, and then the hyperlink points to the root address /LED on with the text that says turn it on. And that's it. Our getHTML function looks complete. Now, let's implement the rest of these functions to actually handle the LED on, LED off, and not found request. So, I'll duplicate this function and change the name to LED on, and then set the LED status to high, and print the LED status on. Again, I'll duplicate this one more time, and then change the name of this function to LED off, and then this LED status variable must be set to low, as well as in the serial monitor. And lastly, I'll create a function for this handle not found. So it is just a simple 404 error page, and then a plain text that says not found. So let's upload our code, and there's an error. Okay, it looks like we're missing a backslash here. So let's try again, and it succeeded. So now we can see the ESP32_AP SSID that we've just created. So I'll connect to this network, and the password is 12345678. And now, to test if our web server is working, first I'll open the serial monitor, and then hit the reset button. And the HTTP server has started. Now, I'll open my browser and then make a request to 192.168.1.1, and there we have it. Our simple web page being served by the ESP32 web server. So, if I click on this link that says turn it on, it requests for the /LED on, and the blue LED turns on, and a response of blue LED status on with a new link that says turn it off. So now, clicking it performs another request, and the corresponding handle LED off function is fired. Thus, we see another response from the web server. So, the ESP32 web server simply stores, processes, and then delivers web pages to web clients. Well, web clients is nothing but a web browser on our laptops and smartphones. The communication between client and server takes place using a special protocol called Hypertext Transfer Protocol, or HTTP. And in this protocol, a client initiates communication by making a request for a specific web page using HTTP, and the server responds with the content of that web page or an error message if unable to do so, like the famous 404 error. So, the pages delivered by our ESP32 web server are mostly HTML documents. Now, if you're good in web development, you might want to apply styles to it. So, I have here some CSS to style the button and the web page appearance. Now, I'll apply my style here for button off, as well as for button on. And again, let's test it one more time to see the effect. Okay, just make sure that we are connected to the ESP32 AP network. I'll open the serial monitor and the web browser, and then perform a request, and a more pleasing web page is served. Again, I'll test all the functions that handle the different requests. So, let's see if the request is not found. And we have the not found message. We can also test it using our phone's browser. Just make sure to connect to the same ESP32_AP network as well. Now, for our programming challenge, try to create a similar prototype, but instead of only one button to turn on and turn off the LED, use 3 buttons to perform 2 different sequences. The green LED turns on when the web server has started. And then, when the blink LED button is clicked, the blue and red LEDs blink accordingly. The button changes its color, and the LED status also changed to blinking. Similarly, when the alternate LED button is clicked, the blue and the red LEDs blink alternately. The buttons change their colors, and the LED status is updated. Clicking the turn off button turns off the blue and the red LEDs and then resets the button's color and the LED status to off. Again, thank you very much for watching, and if you've learned something of value here, please click the like and subscribe button, and don't forget to hit that bell icon to get notifications for every new video I uploaded for this course. See you in the next lesson.